Hi level 3s, we've looked at rotational inertia and angular momentum. Now we're going to look at the rotational equivalent of translational or linear kinetic energy, and it's obviously called rotational kinetic energy. It's like other forms of energy. It can be transformed from one form to another, and it's measured in joules. So an object that is spinning about a center of mass is or has kinetic energy, and the formula is this: Ek rotational, these are all subscripts, is equal to half times its inertia, rotational inertia, times its angular velocity squared. So point number 3, if an object falls and is attached to another object that can roll, then its gravitational potential energy is converted to both rotational and translational or linear kinetic energy. So the potential becomes Ek rotational plus Ek linear. So if it goes down an incline without slipping, then the conversion is to two types of energy. So if we have a solid sphere at the top of an incline at a certain height, and the angle is theta of the incline, then we can calculate that its total kinetic energy will be equal to its translational plus its rotational kinetic energy. From its original potential, we can substitute these equations in, and after a whole lot of algebra, rearranging, substituting, we end up finding that the velocity equals the square root of 10 over 7 gh. So what this basically shows is that the velocity can be calculated at the base as long as the sphere doesn't slip. If the sphere was to slip and roll, then we couldn't use this formula or this thinking to calculate the velocity of the sphere at the base, because the slipping would result in kinetic friction doing work on the sphere and the loss of energy in the form of heat. So when an object rolls down an incline, note that its linear kinetic energy is always less than what it would have had if it only slid down a frictionless incline. And that's obviously because some of the kinetic energy is converted into rotational kinetic energy. In class we'll look at a cylinder, a couple of cylinders, and see what happens dependent on whether the cylinder is solid or hollow. What do you think will happen? Which one will win the race? So if we have a look at the rotational inertia equation for a solid cylinder and then a hollow cylinder, these were the values we looked at previously. So which one will reach the bottom first if we roll them both down the incline? Remember that rotational inertia increases as the mass distribution gets further from the axis of rotation. So for this one on the right hand side, the rotational inertia will be greater. So for the hollow cylinder, it will gain a higher proportion of the rotational kinetic energy, which means there'll be less of the energy left for its linear kinetic energy, and so therefore it will come last in the race. Another application we will look at in class is the flywheel on a bus, and how these flywheels actually store energy, rotational kinetic energy. And another application, the final one, is a yo-yo. So let's have a look at a yo-yo when it's moving down. So this is the string, the tension in the string on the right, and there's a weight force acting through the center of the yo-yo. R is simply the radius to the edge. So the forces acting on the yo-yo mean that Fg is greater than T. So the two forces are not balanced. The net force, which is weight force minus T, does the work on the yo-yo to accelerate it in the linear direction. So in other words, as the string unrolls, unfurls around the yo-yo. And the distance between these two forces creates the torque on the yo-yo. The distance is r, so the torque does the work on the yo-yo to increase its rotational kinetic energy. Isn't that clever? You need to complete the activity 9D, questions 1, 3 and 4.